well, this would actually never really have been on the table if we were talking about real APL. The APL of old, the APL that everybody loves and hates, that they grew up in or maybe they saw in their high school programming or applied math classes, that APL really doesn't compile very well. And there have been a number of research compilers on APL before that looked at this and said, well, no. And the problem is that there are some features in traditional APL that makes it very difficult to compile well enough that the benefits of compilation makes it worth it. You can do it, but you're not going to get the performance that makes it worth it to compile. However, John Scholes added a nice feature to Dyalog APL called Dfns, which essentially restricts the language just enough to eliminate all of the nasty things that we don't like about APL from a compiler's perspective and leaves all the goodies that we do like. So if we have Dfns, that provides a reasonable starting point for a compiler to actually get off the ground. Whereas if we didn't have this, this wouldn't be possible at all. And so let's look at some cases that we actually are concerned about with the compiler. In particular, this is one of the big things that the compiler has to offer is memory management benefits. And this is an example of one of the places where you can have horrible performance. And this is in large scalar computations. And Dyalog already does automatic vectorization. So a single scalar primitive will be very, very fast, often faster than the naive C code if you don't have the right optimizations turn on in the compiler where it does all that pattern recognition. However, this is a line taken from an actual benchmark in APL, and you can find the Black-Scholes code for this on some of the classic APL papers. But this benchmark doesn't run very well because we have a number of things here that really mess us up. One is we have these multiple uses of variables here, and those variables are large vectors. And those large vectors get traversed once for each one of these calls. And they get traversed all the way through. And then you'll notice that all the rest of the operations here are just scalar operations. So really, there's absolutely no reason to traverse the vector multiple times throughout the course of our computation. And if we do the traversal, even if we're using vectorized operations, we're blowing our cache every single time, and possibly multiple times within a single iteration of this vector, and then refilling the cache with the same old arguments again and again and again. And this is one of the primary reasons in the interpreter for massive slowdowns in certain benchmarks for large scientific type of computations. And this is something that the interpreter is going to have a real hard time with. But a common optimization that we can see at this level is scalar fusion, which languages like Accelerate in Haskell, which is a array programming DSL for Haskell, that actually does this sort of operation and can take advantage of the cache to do these operations faster. Now, that was an example type of application, but the overall design of Co-Dfns is not what I call super compilation. Rather than aiming to create really super fast code without any input from the user, Co-Dfns is intended to allow very predictable and safe and controllable optimization with the aid of a tuning expert. So rather than going for this massive, super smart compiler that can interpret all your APL code and then make things go, instead we're aiming for giving the user the ability to do certain optimizations that otherwise wouldn't have been possible without the compiler. And the compiler itself will do a reasonable job of things, but it's not going to try to create unpredictable performance. And that's one of the things that I really am aiming for in the Dfns compiler is trying to eliminate variability in terms of performance when you're using the compiler. You should be able to predict or at least reason about the compiler performance without needing to run umpteen number of tests. So Co-Dfns isn't just dfns. There is one aspect of the language which really is sort of at the heart of the intentions of the compiler, and that's there are two primitives, which are the complete extension to the dfns language that makes up Co-Dfns. And this is essentially the single assignment empty vector. So it's a constant that is the same as a regular empty vector, except its fill argument, instead of being 0, is an empty single assignment cell. And then this is an operator which takes a function and produces the same exact function, except that it runs that function asynchronously and returns a single assignment array, which will be filled with the results of that computation. And when Morten and I were talking, one of the things I really wanted to focus on was parallel performance, as opposed to what a lot of people focus on, which is sort of the optimizing the array expressions. And I care about optimizing the array expressions, but what I really am interested in is making it possible to reason about parallel APL code and make it faster in a sort of controlled manner. So let's look at some examples of how this works. In the simplest case, if we take this empty single assignment vector and reshape it to a 5 by 5, we get back a single assignment vector of 5 rows and 5 columns. And this is exactly the same as any other array, except that all the values are single assignment cells that have as yet been unassigned. And so this is how we construct our, this is the only new data structure that we're adding for parallelism. And it allows us to do basically two operations. We can write once into any given cell. So these are termed called ivars, but we can write any value into one of these cells one time, but then that value is fixed. We can't actually change the value afterwards. And we can read that value out, and it works just like any other standard array. However, if we try to read from a cell that hasn't been assigned, then the computation is going to block until somebody assigns a value into that cell. And then we add onto that the ability to do asynchronous computation, which allows us to actually have another computation running that will write into that cell. And so we won't block forever. And this is an example of parallel each, where you just take each and whatever the function you want to make parallel, you just wrap it up in it. And so for a little more involved example, we have a reduction of a depth 1 vector. So a vector of just numbers, for instance. And we have a parallel reduction. And it's not actually parallel, because the ordering dependencies create a serial chain of asynchronous function calls. But if we look at this, we start by creating an empty single assignment array of the same shape as the input argument. And so we have this empty vector where we're going to put all of our intermediate results into it. And then we basically compute all the intermediate results and store that into each cell of the array. And to do this, we start by seeding the first element with the first element of the input argument. And then for each one of the next arguments in the vector, we spawn an asynchronous function that takes in, basically, for each argument and the index of the previous argument, we then compute our given function that we're reducing over with the previous value and the current input value. And so what we get is a chain of function calls where the second function call depends on the first element of the first element of the vector, and then the next one relies on the results of that function call, and so on down the line. So this isn't actually parallel, because we can only actually execute one function at a time because we're waiting on the result of that for the next function. But it demonstrates how we can use sort of the implicit single assignment property to get a deterministic computation without having to do any semaphores or locks or other kind of structures. And all we need is this single assignment data structure, and we can get a deterministic computation that sort of does the right thing without having to worry about Okay. And importantly, if we, let me see if I can, if we go back to this, if I change this to the empty vector, and I change this and just got rid of this, this function would be the exact same as the regular serial. This would be a valid way to write the serial version of this. And it would work the exact same way. And that's sort of an important property that I want to preserve in the language, is that we can reason about the parallel programs almost as easily as we can reason about the serial programs, provided that a few syntactic conditions are met to ensure determinism. In particular, if we write to any vector inside of a computation and spawn asynchronously on that, those writes have to be to single assignment arrays. They can't be to regular arrays. And if you do that, then you're going to have a deterministic program. It might deadlock on you, but it's going to deadlock deterministically. And furthermore, generalizing that a little bit, why is it so difficult in so many languages to actually reason about performance?
We're not timing, are we?
We're timing.
Oh, never mind.
Yeah. Okay. Yeah. And so, in a lot of languages, it's really, really difficult, especially high-level languages. It's very difficult to tell how fast your computation is going to go. Even in the Dyalog interpreter, which is pretty straightforward, one computation which computes the exact same thing as the other and really looks about the same, unless you know the tricks, there's no way to predict which one's going to go faster. There's not a good mental model for the performance of the system, either in terms of memory or in terms of execution speed. And languages like ZPL, for instance, make a really big point of trying to make sure that you have certain properties that you can reason about that are highly correlated with the performance of your system, and especially parallel performance. So in the case of the language ZPL, which is partly inspired by APL, the two properties they care about is communication, when communication is going to happen from multiple nodes, and how many parallel nodes you're going to end up spawning. And so it allows you to get really good control over the type of communication that's going to happen whenever you do a parallel computation. So you know, in a distributed computing context, when you're going to get, for example, when you're going to have to broadcast to everybody, or when you can send data strictly to a single node and what that node is going to be. And this allows you to actually get some really interesting guarantees about the performance of your system. And we want Co-Dfns to, as much as possible, have that same behavior. And how do we reason about this behavior? Well, we already have APL, and APL is sort of like a math that you can use. And so why not use APL to reason about APL? And this isn't as crazy an idea as it might first appear. Lenora Mullen wrote her dissertation on the mathematics of arrays, which gave a way of basically axiomatically talking about APL using essentially APL as its description. And this is possible in part because so many of the properties that we care about in APL are actually described as first-class citizens in the language. So for example, the shape property, the domains, all of these things, those are all accessible in the language themselves. And so we can talk about them using APL and reason about properties of our programs using the language that we already know. So plans and schemes for this compiler, by the end of the year, we should have a usable version that people can actually start working with. And our intention is to target multi-core GPU and distributed systems, but with a real emphasis on integrating completely in with the Dyalog system right now. This isn't going to be a new system, it's going to be a component attached to the Dyalog system. And the effort is particularly on scalable parallel performance, as opposed to, say, getting the best vectorized code that we can possibly get out of our primitives. And to do that, we're really trying to make it possible for the compiler or the tuning expert to sort of have a dialogue back and forth between the code. So the compiler is not just going to do everything at once and then the tuning expert just makes sure it gives the right code in. Instead, we want the tuning experts to be able to extend the compiler with optimizations that they care about, provided that they can demonstrate those optimizations are correct and safe in some level. And then to allow us to attach properties or contexts to those optimizations, and then and then allow the compiler to use those optimizations that we've given in the appropriate contexts whenever we want to, and have a reasonable assurance that we aren't breaking all of our mission-critical code in our pursuit of the ultimate performance. So while that's a nice scheme, version 1 is not going to have all of that. We're really aiming at the low-hanging fruit optimizations here, things like scalar fusion and good memory management at the lower levels. And then we will use that as a baseline for identifying and optimizing and developing the rest of the compiler from there, as soon as we have a little more feedback on the system. So to compare a little bit about the interpreter and the compiler and what the differences of the system are going to be, the interpreter is garbage collected. Whereas the Co-Dfns compiler, part of trying to make sure that we have predictable behavior, is being able to predict the kind of memory allocations and that we're going to get and how and when those are going to happen. So we're using a stack-based allocation scheme instead of garbage collection to do this. And instead of idiom-based special casing, which we probably will have at some point, we're focusing more on whole program style analysis or interesting general localized reasoning. And we want to try to make machine-checked proofs and verification of code correctness available to APL programmers at large, rather than leaving us in dynamic land with no hope of actually checking or talking about the code. So a common thing that we see in Usenet or in APL discussions is people writing out a long string of equivalencies between various APL programs to talk about how we optimize these things. But there's no machine checking to ensure that those are actually equivalent. And we'd like to make sure that you can write those equivalencies and then have some idea of whether or not they are equivalent using machine checking. And that feeds into the ability to create safe user-defined optimizations, where you as a tuning expert can develop your own set of tools for optimization and work on those tools so that when you get your client code in and need to optimize it yet again, this set of your bag of tricks is already encoded in a reasonable fashion, and you don't have to just store that in your own black arts handwritten notebook somewhere. And the Co-Dfns compiler is going to be restricted just to Co-Dfns. We're not aiming to do the whole APL, and we're not aiming to really implement all of the Dyalog system. We're just aiming specifically for the restricted language and then integrate it in with the rest of the Dyalog system and leverage the numerous extensions that Dyalog supports. So in the end, once all of this is there, or even before that, the last thing that really drives the design of the compiler is that there should be less than trivial effort in order to use it for existing Dyalog customers. So when you pull up your Dyalog session, you just copy in a workspace and you just use the fix function there instead of your traditional fix for fixing one of your namespaces in. And it's provided that it's written in Co-Dfns and not traditional APL, you're good, it works, it's all exactly the same to you. You don't have to do anything else. It just does its thing, and there's no really significant change in workflow just to get and use the compiler. However, that does not mean you're going to get fast code. So you'll be able to use the compiler and we'll give you reasonable results, but we're not a magic act, and we're not going to be able to provide super code just from you taking your existing code. You will have to still have use the tools in the compiler to get these optimizations and to leverage them and apply them. And that's a slightly more manual process in Co-Dfns than in a traditional high-level compiler. So that is one of the sort of caveats of the whole system. So some coding goodies to just talk a little bit about what we have in the Co-Dfns system is the compiler is inherently designed and explicitly designed to allow easy integration with other people's code. And for the first time ever that I'm aware of, it will provide a portable, sort of easily used, complete parser for the Co-Dfns language, and produce it in a format and with a portable AST that can be used by any language and by any system, so that you can actually parse your APL code in its entirety rather than using a limited subset or doing really ad hoc parsing techniques. And I thought that this was something that should have been out there already, but apparently not. Apparently parsers are not a big issue in APL's 40-some, 50-some years of existence. So this, I don't think this should be new, but it appears to be new. And an additional thing is that the Co-Dfns language includes a complete functional specification of the language, which up to now also seems to have been lacking in the system. So when I searched around to find out what the Co-Dfns language actually was, I discovered user documentation, system code, and a lot of old wise wizards that knew how the language worked, but there was no clear, exhaustive description of the behavior of any of these systems or of the language itself and the kinds of responses that we should get. So part of the work in this compiler was to actually figure out what Co-Dfns is in its entirety in exhaustive, gruesome, excruciating detail. And so that is now done and available. And additionally, the compiler is designed to easily support multiple runtimes, so that for any given compiler, instance of the compiler, or any instance of a compiled piece of code, it's trivial to swap in and out at different runtimes, so that you can experiment with different runtime implementations and sort of easily plug and play the runtime you care about. And this actually makes it a lot nicer to integrate with other languages. So if you can write your APL code in Co-Dfns, then you'll be able to easily embed that, for example, into other programming language frameworks, or connect between existing code that might be available as a DLL or as object files or source code with your APL code in a way that's a little bit less restricted than the current FFI in Dyalog. So some acknowledgments. Dyalog has provided significant funding and support for the project over the past year. And a lot of the ideas in Co-Dfns were inspired by things like mathematics of arrays, Intel's concurrent collection system, and a lot of the work on deterministic parallel that goes on at IU. And unfortunately, C++ too inspired a number of interesting things. I hate to say it, but they did. And the design of the compiler in particular is very closely tied with Andy Keep's work on using NanoPass to design industrial strength compilers. So at this point, we would actually demo some of the compiler at whatever state it is, although at the moment, I don't have that demo prepared. Deadlines are horrible things. So that would come into play around this time. And then we're done. So thank you. I apologize again for the slides. Yes, I think.
So how hard is it to convert an APL program to Co-Dfns? I mean, or into dfunds if you don't care about the parallelism.
Very easy to convert functional programs that don't rely on dynamic scope or lots of mutation of global variables into Co-Dfns. Quite easy there. Assuming that you use actual structured programming techniques instead of go-tos.
Okay. how many normal APL programs would satisfy those rules to be? Would you expect that most people would be able to?
I would expect a significant portion of user-facing interface type code not to be portable, but for computationally intensive or high-performance critical type of code to be fairly easily portable.
So is there a way to mark a particular region of the code and say this should be Co-Dfns?
Yeah, you basically
you
abstract that into a namespace.
So you try to get your kernels to be in that format and don't care about the rest?
Right.
Okay.
You basically abstract that into a namespace and then just call the functions from the namespace.
Maybe I have something totally related to that, and I think you were talking about this, but I wasn't quite sure. So it is possible to have interpreted code and then compile. It's in APL.
They interact
and then compile
seamlessly
code
together.
and they
Yes.
can call back and forth.
Yes.
Okay.
Exactly. Yeah. That is part of the support from Dyalog. The Dyalog people will have to alter their system in order to support this concept.
Back and forth, or just back?
No, back and forth.
Back and forth.
Yeah. That's part of the explicit intent of the compiler. You had a question.
Yeah, so there's a slide in the middle without a tiger, and I felt a little cheated.
See, I threw that in there just because I knew that somebody would be expecting tigers in every
When you
slide.
say cheated instead of pump?
I guess it could be.
I think you had
Are you using Andy Keep's actual NanoPress framework or just the ideas from it?
I'm just using the ideas. I really wanted to use the framework, but it didn't work out.
It's really cool, but
Yeah. Part of the reason is that
I
Co-Dfns is
use
written
it.
in Co-Dfns.
oh yeah.
So
Okay.
and the NanoPass framework, it's actually really nice. And if there weren't other compelling reasons not to inject scheme into the rest of the system, I probably would have done it. But it's to reduce the number of dependencies and make it easier to deploy and embed and a number of other things. And I'm really taking advantage of this approach from NanoPass. So I'm basically doing everything except using NanoPass that I can. I think.
Yeah, Jeremy.
You talked about how you're not going to get it's not like a super optimizer right off the bat, right?
Right.
And so there'll be this dialogue and whatnot, and so what will the guy doing the tuning, the performance expert, what will he actually do? Does he write something down? Like, does he add annotations to the program, or does he push buttons in an IDE, or what actually, because you didn't really...
Yeah. The reason I didn't mention exactly is because I'm still that's an open design research question, is exactly the best way to do this. One of the things that I've been playing with already is I have an Isabelle file that allows you to prove properties about the codes of APL expressions. And the idea was if you insert annotations into your code, the compiler will spit out an Isabelle file. And if you do the proofs there, and then I wanted to be able to read it back in. I'm a little suspicious now as to how well that will work.
Actually, so sorry, I think you're describing at a fairly low level of
So,
abstraction what it is that you're doing. So
fundamentally, the process of the tuning expert is twofold. One, to take an example program that you care about optimizing in a certain class of programs, and identifying the salient properties that allow you to do certain optimizations. So things like commutativity, associativity.
Okay, so you're talking about rewriting. Like
I'm
local rewriting kinds of optimizations.
Both local and as global as possible. So things like, and again, the details of exactly how I want to do this are a little open, but the idea would be that if you annotate the program with certain properties, then you are then under some proof obligation to show that those properties hold, and then the compiler can take advantage of those, using optimizations either that are built in or that you have written and attached to the compiler as an optimization library. So the idea is that a tuning expert, after doing this once, for instance, for a class of programs, would build up his own set of optimizations that he likes to use, and then use those. And those could either be shipped or applied automatically to other pieces of code, or be available for use as their own entities. Did that answer the question?
So I have two questions relating to Eric's question. So for NanoPass, so how did you actually end up having something that looks like a compiler that uses the NanoPass architecture, and how many passes did you end up having?
Well, it conceptually feels like NanoPass, but there are passes within passes within passes. So there's a high level concept of passes, and right now I think I have maybe 20 or between 10 and 20 passes that are there, and then each of the passes, rather than being designed on this sort of recursive case-based tree recursion, are doing global passes over the AST to do as much as possible there. So for example, in the parser, one of the passes eliminates additional annotation elements that were used for pretty printing the code. And that's, rather than doing a case tree walk, that's just a single statement that's like an APL expression that blows away all the lines.
Okay.
But I'm confused with NanoPass itself. You don't explicitly recur, you write.
Right, you write these cases, but the cases are at like the individual element level, where, well, I guess I can, should I show you the code?
Yes, show us the code.
So
I want to see just a little.
One moment for me to say, please show more concrete things.
Yeah, the second part of my question was going to be, is it open source, and if not, can it be?
Dyalog and I are actively working to make it as open source as possible.
Okay.
The intent is for academics to be able to take this and easily plug it into, for example, a Haskell library, to use it as a backend for other array computations in other languages, for doing new optimizations or whatever. We want to make it as open for research as possible.
Okay.
So, yeah.
So you said this is written in Co-Dfns?
Yep.
So how do you do like represent trees and things in APL?
So in APL you could just use objects, but Co-Dfns doesn't have objects.
What do you call that comment character that looks
Tombstone.
like? Okay, that's what I thought. It looked like a tombstone, and I was going to say.
So here's a real simple. This will be simple stuff here. So basically, let's go through here. This is a real simple version of the compiler that basically just creates an empty namespace and parses the beginning and end tags and things like that. But it gives the feel of how things go. So the entry function is this fix function. And these states here, when you see state annotations, that corresponds to where in the state space of the specification this line corresponds to. So for example, on entrance into the fix function, the state corresponds to this in the state specification and describes the behavior, what should happen afterwards. So we initialize our foreign functions, and this is the line that validates the input. So that's to say that we have to have a vector which contains vectors which are all character vectors.
Is that an explicit seg fault?
This?
Yeah.
No, that's just an exception.
Okay.
Yeah. Yeah. And then we do some argument handling. And so forth. And so then we call the compiler down there. And
I guess I'm hoping that whether or not you have a live demo, that you will have a.
I'm hoping to put some more examples and code in there, if possible. What would you prefer to see more concrete? Because I would like to put some more.
I want to see a picture that looks like, here's this pass, arrow, here's this pass, arrow, here's this pass, at the very least.
Yeah, is that in the code? In most NanoPass compilers, there's some place where you compose the passes.
Oh, that's there. So this is a simple version.
Tokenize, parse, gen LLVM.
Yeah, so this is a real simple.
Okay.
This is like a 3-pass compiler.
It's like the Rust compiler.
Yeah.
No, so this is a really this doesn't have all the extra.
Okay.
This just has the first 3 passes in trivial form.
And really, doesn't it have one, because tokenizing and parsing are not really passes.
Parsing is actually 3 passes nested into one another, because parsing is one of the most difficult problems of the APL compiler, because you can't parse without knowing the types of the variables that are bound. So there are 4 classes of bindings. There's an array binding, there's a function binding, there is a monadic operator binding, and a dyadic operator binding. And so how you parse the system depends on whether the variable bound is one of those things. Now, most of the cases, it's
cool.
pretty unambiguous. But the fun case,
You just said that?
That's one word for it.
the fun case is
Do
this
you work
one
with C++
here.
by any chance?
Did you see the note of C++
Reinvent
in my, I had to mention C++.
Yeah, but it was
So
derogatory, right?
Yeah.
Yeah. So you get this here. Now, if A is a function, clearly B and C have to be parsed as the right argument to A. But if B is a function, then A could either be a function or a value. And if it's a value, it's the left argument to B. But if it's a function, it's the application of the result of applying B onto C, right? And so forth.
So does that mean things are strongly typed?
There's a lot of type inference in this compiler.
But I mean, everything does have a type. You can't dynamically change whether something's a function or not.
It sounds
Yes,
like
so
there's
you
four
cannot
types.
you cannot bind a variable to a new class of value within the same scope.
Okay.
So if you start with an operator, it's got to continue to be an operator of that form. I could go into more scary, horrible
It sounds
details.
like the parser has used up a lot of effort inside the compiler. But
Indeed.
but what works in terms of parallelism now, and what is
So there's no
continuing to work
parallelism
by
in the
demo?
compiler right now. That's going to be added sort of at the later stages.
When you
once the
showed
list-
that initial line of code, I was expecting that to be a running example that says, hey, and now if it's so easy, with less than trivial effort, you'll be able to take this piece of code, perform the following fiddlings to it, and then you get fast code out of our compiler.
Yeah, actually, that'd be a good idea. So that's an
Right.
example where the
Yes, it
compiler
would be.
should automatically handle everything.
Oh, that's even
Right.
better.
So yeah. So show it morphing or whatever.
Yeah, so the compiler should automatically transform that into a scalar fused operation.
Great. Please say that.
Show it.
Good point.
Yeah.
Yeah, I should show that. I should.
Yeah.
I should.
So, yeah,
and
so-
if there are other fiddlings, again, I will hope to see an example
So-
of a line. And
Okay.
oh, it's too bad if you compile today. That's what horrible. thing
Yeah,
will
I've got
happen.
2 or 3
So,
examples. I
When
could
you
probably
say
fit in on
performance is
that.
not free, great. Give an
Okay.
example.
All right. Yeah, that's probably a good idea.
Right, and this might be hard, might be a problem with me since I don't understand the code in the example, but maybe you want to highlight the parts that are bad. You know, what parts in that code are suboptimal, or
So-
would the audience just know that because they know what the code
Yeah,
is?
they would know that, and actually the entire thing is suboptimal. That's kind of cool.
Okay.
Really, all of it is that really highlighting none
So
of it.
speaking of suboptimal, was there a reason that the parallel reduction example wasn't using a binary tree topology? It's fine
Yeah,
you have to
for
commit to a topology.
simplicity's sake. I could show more sophisticated.
Well, but it wasn't simple because it made you spend several minutes explaining why it was a parallel example that wasn't parallel.
Yeah, but I wanted to do that, actually. I wanted to have an example that demonstrated the dependencies of the system. I could have written it another way that would have hidden those details away, but I was kind of hoping for an example that illustrated how the dependencies on blocking and reading and all of that work.
But is it too much code to do one with simply a different topology for the reduction tree?
It would be multiple lines.
Two
That's
lines,
a
work
no-no.
for 2 lines?
Well, so I could actually do that if we wanted to see a tree example. We could do that.
And you can't write a helper function or something that makes it so that it's
You
2
can.
functions, 1 line each.
Yes, I guess I could do 2 functions, 1 line each.
Can APL do recursion?
So-
Yes.
Okay.
Yeah, I think there's some higher level things to think about. There's so
Before you remove this code,
there's a lot. I mean, I like overall. I like the talk. One thing I would kind of go through it and think to yourself, are there places where I'm just sort of telling the audience something and hoping they believe me, or am I actually showing them the evidence
Okay.
of what I'm trying to prove to them, or so for example, you start out by talking about interpreter limitations, and that seems to me like okay, if they're, I'm guessing that they've all been living in a world where there's just this interpreter and that's it, right?
There are interpreters and
Right. So there's
research
multiple different
compilers.
interpreters. So it'd be really cool to see like a graph showing how bad the performance is for a particular nice little example that you care about.
I
Right,
could
or
pull that up.
or
and,
just
and what it would look like compiled.
Yeah, so I've got one example from a couple of benchmarks where
Yeah.
if it's wrong, it's like 100 times slower. If it's correct, it's as fast as the C code.
Right, and show maybe little snippets of code that Dyalog can't optimize for some reason. Maybe because
So you want
it
more
only has
examples
local
of that than just
information.
the single scalar version, like lack of segments in scan.
Well, no,
I've got a bunch of different
The question is
sparse
what's most
magnitudes.
effective for your audience. And I'm thinking that it's possible that if you, instead of naming the problem in English, if you show for each problem instead the APL code, that will be slow. First of all, it probably will be shorter, and secondly,
Yes, okay,
it may be more direct.
Yeah, no, actually, yeah. So
the
everybody in APL is
Yeah, it
familiar
would
with
just be
where
Especially if you can get like as short as possible.
I could do that.
So, because like the one example, it's like, okay, black shoals, like that's cool. But I mean, anything where you're like, oh no, I have to do multiple traversals because I'm doing a stupid.
I've got a
and
sparse
you can do that
matrix
in
vector
like,
product
like
that
5 ops
does
or
that.
something like that. I mean, you can make it like.
How about normalizing
Really
the
quick.
vector so the average is to 0? Isn't that 2 traversals? Or can you? I guess that has to be 2 traversals.
Normalizing of I'm sorry, I don't even really quite know what that.
Never mind. I was thinking of adding a constant to each element of the vector so that the average of the vector becomes 0. But maybe that requires 2 traversals, so it's not a good example.
Well, if it's 2 traversals, it's a good example. It's
Maybe
not a
very
great.
computing the mean and standard deviation of the elements of the vector.
So mean is actually pretty fast.
And standard deviation is also pretty fast, but why do I have to traverse twice?
Yeah, so it's the twice that so maybe if there's a way to okay. Yes.
But a completely different thing. Signal. I'm assuming that signal 2 is like syntax error or error or something.
Domain error.
Right. In the comments, you explain exactly what the error is, and then you lose it all by saying signal 2. Why don't you give the users really friendly syntax errors, telling them exactly what the mistake was?
Because I'm matching precisely the observable behavior of the existing interpreter.
They're producing the dumbness of the pre-existing
So if
system.
they get this error when they do it the one way, they should get the exact same error if they do it the other way. They might get it ahead of time, like they might get it earlier in the compile time instead of runtime, but they will still get the exact same error. Yes.
So I assume your audience is familiar with APL and not Dfns.
Most of them will have seen Dfns.
What was Dfns used for in the past?
It was John Scholl's toy initially. The Dyalog said, you're crazy, all right, go ahead and have some fun. And then he wrote this thing and everyone went, oh, wow, hey, wait a second. Programming languages design actually knows what they're talking about with lexical scope and things like easy tail recursion and the like. And so it became the predominant preferred form for all new code, basically.
Well, you might want to put up a comparison chart maybe of things that are missing, how you do things differently. In case there's somebody who hasn't seen it. Just like, you might think everybody knows what the problems in the interpreter are, but I'm sure there are beginning APL users or whatever who haven't done these things for years and don't know all the expert level problems.
That's a good one. Yeah.
A couple of questions.
Yes.
Who created Co-Dfns?
I did.
Okay.
At one point, it wasn't entirely clear, because at one point it sounded like you were saying, I went out to try to find documentation on Co-Dfns and I couldn't find it.
Oh,
yeah.
So,
true, okay.
So that
really, so I thought for sure it was someone else at that point.
No, well, okay, that's a good point, because basically it's Dfns with those 2 operators added, or those 2 signals.
Okay, so you were actually talking about Dfns at that point.
Yes.
Okay.
I should be careful about that.
I think that happened a couple of times. I was definitely under the impression Co-Dfns was being already.
I think really like drawing a kind of hard and fast distinction between this is Dfns, this is prior work, and why it's cool.
Right.
And then this is Co-Dfns.
Yeah.
This is exactly what I'm adding.
If this were
like a number of times, like it wasn't entirely clear. Okay, how much of this was prior work, how much of it is your work?
Yeah.
And like some of it, like the 2 operators is like okay, like that was clear, but like it's really good to sort of if you can solidify like which is which.
What was the upshot of the prior work? Did it yield better performance, or was it just?
It made it
the
possible
language?
to compile APL.
I see.
Right.
Have a
So
shot.
crazy language that can only be interpreted to sort of more.
So this is like the hip hop VM at Facebook. They have PHP and they have Taint PHP. Taint PHP is a really good presentation.
And Aaron, one last question. So you use the term scalar fusion a whole bunch of times. And that kind of confuses me. It almost sounds like an
Deforestation, right? Fusion deforestation.
It sounds like an
Extreme fusion.
oxymoron. I know what fusion is, and I know what scalars are. and scalars are things like 3.14. Okay, and fusion is this thing that you take two loops and stick them
I
together.
think scalar means element-wise operator.
Yeah, so scalar is a term for maybe I should say scalar function fusion.
We're not your target audience.
Will they know what this is?
I think that they will know, but that's actually a good point because scalar, we talk about scalar functions and then we talk about scalars, and maybe it is useful to disambiguate that.
Could you
But
just
am I
say
at least clear on that? So scalar functions are all maps, right? They're all element-wise operations. And
They're
scalar
deep
fusion
maps.
is fusing maps.
Scalar functions are deep maps.
Okay, they're maps that ignore rank.
So scalar functions are things that don't work on scalars, but instead work on lists.
So remember, everything is an array in this language,
of course.
and so even scalars are arrays. And so a scalar function is a function that is defined based on the scalar elements and the mapping from the input scalar elements to the output scalar elements, regardless of shape or depth.
It's a parametric function.
Well, it's data generic, right?
Generic in the shape. Oh.
It's map until you find scalars.
Yeah.
There's a deep map operator I can write that describes
This is just a part of his translation, but if you just call it fusion,
actually, maybe fusion is a term that everybody around here probably knows, but maybe they don't actually.
Well, you might want to have a picture too of the original program
Call
and
up some of
then.
your APO friends and ask them what terms make
That's
sense.
why this is being recorded and sent out to
Okay,
them.
great.
And if they don't know what fusion is, or we had a slide that listed optimizations. If they're not compiler people, they may not know what any of those are. So you might want to show those things instead of just listing them.
Yeah, true.
Yeah, and especially like with the fusion stuff, like you can make a beautiful picture,
Yes.
Just like, okay, well here's a vector, and then I have a little animation where I'm walking along it a bunch of times,
it'd be
and then
really
be like,
easy.
oh no, well, how about I just keep more information and walk across?
Yeah,
the
actually,
board?
that would be really
that would
good.
make a great animation to just make it blatantly obvious what's going on.
Right, and maybe APL code before and after.
Yeah, actually, the APL transformation is pretty straightforward. So showing
You might want
that
to show
is-
both.
Yeah. It's literally wrap it, deep map it, done. So.
Right, but you didn't show the code for that.
Yeah, I didn't. So I should. That's a good point.
And for many of these other ones too.
To answer a question I think was asked was how am I encoding trees in APL? It is as a 4-column matrix. First column is the depth. Second column is the name of the node. Third column is any textual data. Fourth column is any attributes attached to the node.
And how do you get the hierarchy then?
What?
How do you get the
The
hierarchy?
depth. The depth in the first column.
But how do you know what's linked to what? Is it ordered
Left
by?
to right
It's
child.
XML.
Okay.
Yeah. It's XML.
But it is actually then order. It's depth first traversal then, and so the order in the vector matters.
Yes, it's depth first traversal and ordering within depths. Yeah, order matters. Yes,
Yeah,
yes.
okay.
So it's XML, which is actually one of the benefits of this format is that Dyalog already has an XML converter from this format to XML and back and forth. So if your language can read XML, then it can spit out an AST that this compiler can slurp in and then use at any point in the compiler, because every pass can be ugly printed as XML.
I saw the popular representation of trees in array languages is a list of a vector of parent pointers.
A list of a vector.
Like a vector in which each element is an index.
With the links to the indexes.
Yeah.
That's an alternative representation. It turns out not to be as useful here because our traversals often are depth first traversals when we're writing
Top
a
down.
compiler. Top down, yeah.
Top down.
And so, for example, like this one, I have a tree at this point. I have a tree with tokens, lines, and then strings of tokens within each line. And so this expression can just extract out all of the token content values.
So this is where a specific depth has a specific meaning, rather than you can embed one expression inside another expression and it will still make sense.
Yeah, so if I have like tokens, and then I have line
Right.
here, and then I have some token here,
Right, but you don't have lines inside the token. You don't have many lines inside a token.
There we go. There we go. Like that. That gets converted into 0 tokens, empty. I'll just draw the box for it. 1.
So I guess I'm more wondering how you would encode things for not this kind of tree, but let's say SSA or normal.
SSA, which
Well, or whatever you have.
yeah. So
Like would you if you're compiling scheme, let's say.
yeah. So for example, it's just an XML language. So we have. So instead of tokens, we have a namespace, and inside the namespace we have either expressions or functions, and then inside of that expression tag we have various types of expressions that contain variables, numbers, function expressions, and so forth. So actually,
So what's the big of, I can't help but ask this as a teaching data structures this semester, like when you say, give me the children of tokens, I guess that's a function that's going to be big O with respect to the size of the subtree underneath tokens?
give me the
Yeah, because it's just an enumeration of a chunk of elements.
So
You have to have a counter probably that
so you
scans along
can't,
it
so
to
you
tell where
can't
the
get
end
your
is.
children in constant time.
Well, you have a
it depends on whether you maintain a mapping.
But I guess if you're always going depth first, you don't care.
So if it really matters that you need to be able to jump to the children, you can pre-compute a jump table basically, and then you'll be able to. You generate that other data structure,
Okay.
and then that you jump from that. Let me see if I can pull something up here.
And you can do it in logarithmic time if you have a PRAM. So
Let's see.
that probably doesn't help your students. But
Well, thanks, Jared. This is neat to see. It's like a window into a different world.
All right, so this is the language this is the actual AST that's being computed, and this is sufficient to represent all of APL. So at the top space we have namespace, and then namespaces can have inside of it lines, expressions, functions, and function expressions. And then lines just contain streams of tokens, expressions have various forms, and based on what class it is, depends on what ordering we expect these to come into. So
when you say depth, is that really a number?
Yes.
I mean, so if one function expression contains another function expression, then the contained one will have depth one more
Yes.
than the container one?
Yes. So it's a very weird way of thinking about structured data, but it does have some benefits in that certain types of traversals are really, really easy to write.
Yeah, I
as
just
a
don't know
single
why I
function.
want those traversals.
Well,
I mean, you gave an example of that kind of data in sort of parsing stage, so I'm more interested in, what about, how would I write CPS?
Well, so for example, one of the optimizations might be scalar optimizations, right? I can traverse and find all the instances of all the scalars in all the code and identify where they occur contiguous to one another within the program just by doing a full, complete traversal down the thing without having to do any recursion. And it's just a single pass, a pass over the structure. And then I can identify all of those regions that need to be scaled, and then I can scale them.
Because foldable constants basically for a binary operator are just going to be a particular pattern of 3 elements. You can have 3 depth values you can search for where the first one is.
Right, so I can just extract all of the scalars in their relative locations, eliminate the unnecessary pieces, and identify all of them.
And then you can compress things and expand too locally by just inserting into the middle of your vector.
Right, and I can just expand and contract whenever I need to. So it makes the code look very different and feel very different than a traditional compiler, but it is largely just pass after pass of the code, over the code. It's just that some of the passes are really micro passes.
Okay.
One pass might only generate a bit vector mapping certain things over.
Right, and I guess the nanopass mostly is based on depth first traversals.
Yeah. I mean, the entire idea of nanopass is largely making it easy to do depth first traversals.
So, and you have a data structure that's very good at that, so.
Yes. Now, it doesn't mean that there aren't places where you can be wildly inefficient. However, one of the design goals right now is not to make the fastest compiler known to man. It's to generate good code. So later on, we will look at optimizing. One of the reasons the compiler is written in Co-Dfns is actually so that I have a really good instance of excessive memory management possibilities. So basically, in writing a compiler, there are lots of potential gotchas in terms of memory management in an APL system if you write in dfunds in a pure functional style. And those are exactly the kind of places where I want to be able to put my annotations and get good memory management out. So it serves as sort of a large benchmark.
Well, but it sounds like your linearization actually would help a lot of that. Because it
can
means
help.
you don't have fragmentation.
Yes, there is
You're
no
making a
fragmentation.
bunch of vectors, one for each pass, but they're big.
So actually, thanks to Ed Amsden the other day, I implemented the 3.11 interpreter. Ah, where's my mouse?
It's up there.
There it is. Okay. So, all right, so this is the C311 interpreter in APL, and this actually is a really good benchmark because it demonstrates a terrible memory usage performance that the interpreter is going to blow up massively on. Precisely because of extending the environment. Because we do the worst possible case of extending the environment when we're dealing with these flat arrays, which is to basically extend it by one element. So if we look at extend, we take it and we add on one thing to the end of that array. So in the semantics of APL, if you don't have anything that's doing something smart there, you're literally copying the entire array on every single call to that. And because this is a tree that creates a tree of environments, you're completely destroyed. You're done for in the worst way possible if you just go with this. Now there's a way to rewrite this that is very efficient in terms of that usage. But this is the naive interpreter that you can write in about 5 minutes, basically. And you shouldn't have...
I like this code.
I'm glad you showed this, because this is the closest I've ever come to understanding an APL program.
This is the first APL code I've understood today.
Yep.
Well, I'm glad that I was able to provide...
Yeah, I mean, if this doesn't scare your audience, maybe you can show it as...
You switch that character and you transpose that character.
I mean,
the mirror image of the delta.
I mean, maybe you can even show this, even though it looks too readable compared to the other examples.
No, this is good for us.
This is good for you, as they will have no idea or no context for
You
the
can
3
tell
lines.
that it's good for us because it's multiple lines.
Yeah, see, look, this function is even 4 lines.
It has whole strings, too, not single characters.
Oh, yeah.
Or
and it's
numbers.
got long variable names.
Is that allowed in APL?
Yes. However, what is horribly not allowed, which makes me very upset, is that I'm not allowed to use non-ASCII characters in my variable names.
Really?
Not just that, I cannot use non-alphanumeric characters in my variable names.
Wait. So they use all these Unicode characters, but you're not allowed to use them.
Exactly. It brings the whole concept of being at the same level, the egalitarianism of the language
I'll be
implementer.
okay if the ones
and
they
the
use
user.
you're not allowed to use. But if the ones
Yeah.
they don't use...
Exactly, no, and you're not allowed to use them. Which is like, so actually that is an extension that will be coming, yes.
One thing you claim, you're saying that predictability of performance is a problem.
Yes.
Well, so you made that claim. I don't know if I believe, so and you must be referring to the interpreter, or what was it that was unpredictable?
In general, I actually have this complaint about a lot of programming languages. In particular with APL, I have this complaint about a system. So for example, let's say that I have, well, like my
So let's try not to be too general because
Yeah,
this talk
so-
is about APL.
Yeah. Well, so let's say that I have, let's say I have my data structure that I was working with.
Yeah, you don't have to give me an example now, but your claim, so your real claim